Okay, here's a brief little video going over how to do some simple molar calculations. This is stoichiometry, so what we're trying to achieve here in this video is determine the mass of other maybe reactants or products within a chemical reaction. And so we'll take a look at this example here. This is mercury oxide right here. Also a form of mineral called calx, and it's possible to separate the oxygen off the mercury by reacting it with carbon in what we call a smelting reaction. We'll say in this case we have 250 grams of mercury oxide, mercury 2 oxide, and we want to determine, maybe in this case, number one, the mass of carbon that we would need. That would probably come from graphite in order to run the reaction, and we can see, we'll figure out how much mercury we actually get out of the reaction as well. What would be interesting is to for you to determine the amount of CO2, because this would be carbon dioxide as a gas, and that would be what we would call a carbon footprint, because that carbon dioxide would go in the atmosphere, and carbon dioxide is a greenhouse gas. So the mercury oxide is a solid as well as a carbon, and so we're going to get right to work. First thing we need to do is balance this equation. So we can see over here that we have 2 oxygen atoms right here, and on the other side we only have 1, so we're going to need to do a little bit of balancing. So I'm going to say that we'll have 2 units of mercury 2 oxide, and then that'll give me enough oxygen on both sides to balance, and then I will need to have 2 mercury atoms on that side so that my atoms of mercury balance and my carbons are good, 1 on each side. So now that I've done that, I can start to determine my moles of mercury oxide. So my given, this is what's been given here. If I've been given a mass, then I can go from mass to moles. So I do that by finding the molar mass first, because the molar mass is kind of like the bridge between the two worlds, the world of mass and the world of moles. And remember, moles, we use our ratios here, our molar ratios. So we know that if I put in 2 parts of mercury 2 oxide, I'm going to get 2 parts of mercury atoms coming out. So if I had 2 moles of mercury 2 oxide, I'm going to get 2 moles of mercury atoms coming out of that. And then I could use molar mass to determine the mass. We do understand that there is 1 and 1 here. So our ratio is 2 moles of mercury oxide to 1 mole of carbon atoms will give me 2 moles of mercury atoms to 1 mole of carbon dioxide. That's my molar ratio. So let's go back and let's do some figuring out. So I need to find the molar mass of mercury 2 oxide. So I add up the atomic mass, but we're going to call it molar mass, of each atom within that compound. Just within 1 unit of the compound, not the 2 units. We don't worry about the coefficient out front. So 1 mercury atom is 200.59 grams per mole. And there's only 1 of them, so I only worry about that. And then I have 1 atom of oxygen, which is 15.994, and we're going to round up to 16.00. We'll maintain significant figures to 2 decimal places, grams per mole. And so we're going to get 216.59 grams per mole of molar mass. So if I want to find moles, I just divide my mass by my molar mass. So I just need to plug everything in here. 250 grams divided by 216.59 grams per mole. And we can already see that we're going to get just over 1 mole. So 250 divided by 216.59 equals So we get 1.15 moles. And what I'll do, just to make sure that no one freaks out about sig figs, I'm going to put 2 decimal places there to represent we'll just say that we measured that to the nearest hundredth of a gram, and that way I can maintain my 2 decimal places in my answer here for moles. So next up, if I want to find the the mass of carbon, I need to use my molar ratio. So I'm going from 2 to 1. So that means I'm going to need half as many moles of carbon as I have moles of mercury oxide. So if I want to find the moles of carbon, I take the moles of mercury oxide and I multiply by 1 over 2. And I always tell kids, you multiply by where you're going to and you divide by where you came from. So we're going to 1 and we came from 2. So I take my 1.15 moles and I multiply by 1 over 2 and I get 0.58 moles. Alright, so I now know my number of moles, and my molar mass of carbon is 12.01 grams per mole. So I know my molar mass and I know my moles. And if you're an algebra person, what I'll do is just up here, I'll write the formula out. So moles is equal to mass over molar mass. And so if I want to switch this around and solve for mass, I then just manipulate the formula. Mass then would be moles times molar mass. And just pretty simple. You just take the molar mass, multiply it on both sides to get rid of it underneath the mass. There you go. Bob's your uncle. Okay, so now to solve for mass, that's going to be equal to moles times molar mass. I plug everything in here. 0.58 moles times 12.01 grams per mole, and I'm going to get 6.965, so I'm going to have to round up to 7.00 grams. All right, so not a lot. We don't need a lot of mass of carbon. And remember, 1 mole of carbon would be 12 grams, and we don't need quite a mole. We need about 60% of 1 mole. That's what 0.58 would represent. And so that's about 7 grams. 7 out of 12 is about 60%. So now if I want to go a step further and say, okay, well, how much mercury would I have? Well, again, I need to look at molar ratios. In this case, it's 2 to 2, which is equal to 1 to 1, right? So I know now that my moles of Hg is going to be equal to my moles of HgO, mercury oxide, which is 1.15 moles. My molar mass of mercury is 200.59 grams per mole. So if I want to find the mass, I take my moles times my molar mass, and I'm going to get 1.15 moles times 200.59 grams per mole, and I will get 230.68 grams. All right. So there we go. Now we know how much mass of mercury we're going to get. So what you could do, just to check, for a little more practice, is try figuring out the mass of carbon dioxide, which would end up being your carbon footprint. And then I'll give you a hint. The law of conservation of mass should govern the mass of reactants and the mass of products in this case. So you could check and make sure that follows by adding up all the masses of the reactants and all the masses of the products, and it should be bang on. It may be off by a tiny bit due to rounding, but it should be extremely close. I hope this helps.